Welcome back, everyone. We're beginning Module 15, and Module 15 is about light and also the electromagnetic spectrum and electromagnetic waves in general. So light is a very interesting type of a wave, and it behaves in some ways like a wave and in some ways like a particle. And in fact, early on in studies about light, there were tests that seemed to indicate that light was a wave and others that seemed to indicate it was a particle. But it really behaves a little bit like both. So what type of wave is light? Is it a transverse wave? Is it or is it a longitudinal wave? It's a special kind of transverse wave, and it's called an electromagnetic wave. An electromagnetic wave is a transverse wave composed of an oscillating electric field and a magnetic field that oscillates perpendicular to the electric field. So I'm sure that made a whole lot of sense to you. But we'll talk about a little bit what that means. So let's just quickly review what is a transverse wave. That's going to look like a wave of the ocean, and it oscillates the medium it travels through. In other words, it moves matter as it travels in a certain direction, and if, let's just pretend it's an ocean wave, then that would be vertically oscillating, moving up and down the water through which it is traveling. But then it propagates, meaning it travels, in the case of an ocean wave, horizontally, but whatever direction it's traveling, it'll be perpendicular to the direction it's oscillating its medium. And again, a medium is simply what it's traveling through. In the case of an electromagnetic wave, you have two different transverse waves in action. And these two different transverse waves, it's hard to tell, but one of them is purple, the other one is orange, just to show them apart. The first one is going to be an electric field, and the other one is going to be an magnetic field. You may recall that I'll make this one electric. Doesn't really matter which one I do though. So the purple will be electric, and then the orange will be magnetic. You may recall that it's not the electric force, it's not the magnetic force, it's the electromagnetic force. James Clerk Maxwell, who was kind of the early master of the electromagnetic force, was also the one who realized that this is how light waves function. Scientists were running into a problem, which was they were trying to figure out how a wave could travel without a medium, because a transverse wave of ocean water can actually travel only because it's oscillating water and propagating through it. And sound waves, as we've already discussed at length, cannot travel through space because they need to oscillate a solid, liquid, or gas, or some kind of a medium through which they're traveling. There needs to be matter for a wave to travel through. So how is it that light can travel millions and even way beyond that in the case of the stars, miles, billions of light years through our universe, if it's traveling through empty space, if there's no medium for it to travel through, when another kind of wave like sound can't go anywhere through it because there's no medium. So it turns out that the medium, if you're thinking of it as a thing that is oscillating, what you really have with light is you have two fields, an electric field and a magnetic field, that are oscillating with each other. And so that's how light can travel through space. So one transverse wave, which is a magnetic field, the other one, which is an electric field, and they're moving perpendicular and kind of alternating with each other. And so you got an oscillation happening between the electric and magnetic fields as light is traveling, propagating in a certain direction. And this is just one type of electromagnetic wave, but anytime that you have electromagnetic waves, it's going to be this model of having a magnetic field and an electric field oscillating. We can now talk about the speed of light. So the speed of light is rather fast. As a matter of fact, Einstein's theory of relativity determined that you can't get anything with matter to travel faster than the speed of light. You may recall that light doesn't have any mass. So it's pure energy, and if E equals mc squared, energy equals mass times the speed of light squared, then what that's basically saying is that anything with mass cannot actually reach its full velocity until it's converted into energy. And so light is pure energy and therefore can travel at the speed of light, which is through air going to be roughly 300 million meters per second. 300 million meters per second. So when you hear that something is a light year, then basically we're dealing with the maximum speed of light, which by the way is going to be through a vacuum, and so which is basically the same as air. It's roughly 300 million meters per second. So imagine something traveling for 1 second and it goes 300 million meters. So that's 3 million kilometers. And then imagine that doing that for a minute, multiply by 60. Then imagine that for an hour, multiply that number by 60. Then imagine that for a day, multiply that number by 24. Then imagine that for a year, multiply all of that by 365. And that is how far 1 light year is. It's the distance that light travels in a year. So light through a vacuum or air will travel roughly 300 million meters per second. You may recall that sound waves will travel faster through a solid than through a liquid and faster through a liquid than a gas. The opposite is true of light. Light is going to go fastest through matter that is less dense, whereas sound travels faster and farther through matter that is more dense. So air, and they say this is air that is about 25 degrees Celsius. It's going to be this speed. Alcohol, I assume this is rubbing alcohol, 225 million meters per second. I'm not going to put everything up here, every substance they say, but I will say this one. Fresh water, I'll just say water, it's going to travel 220 million meters per second. And let's take plastic, because you do see light through some plastics, clear plastics. Of course, there's different densities of plastic. Lots of different kinds of plastic. It's about 189 million meters per second. And crown glass would be, I'll just say glass. That'll be 185 million meters per second. They say that flint glass, not sure what the difference between the one and the other is, but flint glass is 175,000 meters per second. Now, interestingly enough, diamond, I'll put this way up at the top because I think we've run out of space at the bottom for what the camera can see. Light travels through a diamond at the speed of 125 million meters per second. And of course, diamonds are pretty dense. So going from air to water, you're losing about 80 million meters per second. Then going from water to something dense but still transparent like diamond, you're losing about 100, almost 100 million, my goodness, meters per second. So that's a significant change. And the speed of light then, remember that it is going to be the fastest that anything can travel. Now, in any kind of a science fiction show where they go like, warp speed or whatever, and they go like, a bajillion light years in an hour or whatnot, that's a totally different thing going on. Warp theory and wormholes and that kind of stuff. It's all about basically creating a shortcut from one point in space to another. It's not about actually traveling that distance. But it doesn't really make sense for anything to, with mass, to travel at the speed of light. So take like Star Wars or something where they have a hyperdrive and they jump to light speed. Notice that their ships, like they all kind of like blur out, and the idea I would assume is that they're being converted into pure energy and then kind of reassembling themselves on the other side. Now we're going to talk a little bit about different wavelengths of light. And interestingly enough, or of the electromagnetic spectrum, I should say. So interestingly enough, there's more packed in sunlight than we actually see. What we see because light reflects off of an object and then bounces into our eyes. And we'll get into more detail about that later. But everything we see is simply because, and I see other things going out of focus, the camera's going out. See, focus on that, come back to me, okay, whatever. Ironic timing, I guess. But what we see is because light reflects off of objects and then bounces into our eyes, into the back of the eye where we can perceive it, and translate it into a signal our brain interprets. But anyway, so the visible spectrum contains all the colors of the rainbow, which are red, orange, yellow. That's actually a light green that I have, and I see this is still out of focus, but all right, let's just see what happens if I mess with that. I don't know why it's doing that. It does that sometimes, as I'm sure you've noticed. Red, orange, yellow, which is actually light green because I don't have a yellow marker. Green, blue, indigo, and violet. And what we're doing is as we travel on the electromagnetic spectrum, over here, you can't really see it, but this says big wavelength. Ah, there we go, okay. And that's the lambda sign, which means wavelength. It's the Greek letter lambda. And so over here we have large wavelengths of waves. And then over here we have small wavelengths of electromagnetic waves. So what happens when you change the wavelength of a wave? You're actually going to affect its frequency for reasons that we discussed in Module 14. So in other words, the difference between all of the different things on the electromagnetic spectrum is their frequency, but that's going to be determined by wavelength. So over here you got great big transverse waves that are oscillating electric and magnetic fields, and over here you got little tiny ones that are oscillating electric and magnetic fields. They're all electromagnetic waves. So when we travel outside of the electromagnetic spectrum, which by the way, or visible light, sorry, on the electromagnetic spectrum, everything that we see is Roy G. Biv. So it's just kind of a name you can use to remember Roy, which is a real first name. G could be like a middle initial, and then Biv. I don't know what Biv is, but whatever. So it turns out the frequency of sound, you may recall, determines its pitch. And in the case of electromagnetic waves, the frequency will determine what type it is. And you may also recall that in sound waves, the higher the frequency, the more energy it has. So higher pitched noises have higher energy. Same thing is true here. The frequency is going to affect how much, it's gonna indicate how much energy the wave has. So if you want to, if you are being hit by radio waves, which by the way you are, don't panic, because these are very low energy waves and they're not doing anything to you. But that is at all significant. Over here though, gamma rays are very high energy. If you get hit by these, you'll get turned into the Hulk, apparently. But no, it'll cause cell damage, so you don't want to be hit by them. As a matter of fact, ultraviolet rays, which are just outside of the visible light spectrum, those have enough energy to actually cause sunburn, as we've discussed in an earlier module. So we'll talk about each of these a little bit. So we'll start from red and go outward. Remember that infrared light is actually heat, and it's just a little too red for us to see. So when something is hot, we see it glowing red, but what we don't see is that it's actually emitting a lot of infrared light too, and that red that we see is just going to be that little bit of it that is not quite infrared, is just red in the visible spectrum. So the wavelengths are a little bit smaller. Then going out from infrared, get bigger wavelengths, and it becomes, you move on to microwaves, which is Basically, when you have a microwave oven, what it does is it shoots microwaves into your food, and then those react with the water molecules in the food and cause them to vibrate. And as they vibrate, it generates friction that then heats up the rest of your food. That's why things cook differently in part. I still haven't figured out what makes a microwave work really well with some foods and not with others. But one of the things is going to be the water content. That's going to be one of the factors. Then we have TV waves, so television waves. So those are bouncing around from TV stations all over the place, and if you have an antenna, then your TV will pick it up and translate it into sound and images. And then radio waves are going to be the biggest ones, the biggest wavelength. And those, of course, are bouncing all over the world, again being emitted by radio towers and picked up by radios, translated into sound. Over on the other side, after violet, we have ultraviolet, which you talked about before. That's in the sun and it can actually harm your skin, cause sunburn. And then we have X-rays. You know what those are? You basically blast those through your body, and they'll hit harder tissue like your bones and bounce back. So they'll penetrate. They have enough energy that they penetrate your skin and muscle and all of that, and then will hit your bones and bounce back. And remember that the way we see light, or the way that we see anything at all, is because light bounces off of it and hits our eyes. In the same way, the X-ray machine is going to bounce the X-rays into hard tissue like bones, and then it's going to bounce back and be picked up by the machine, creating an image. And then finally, gamma rays, which we talked about before. They're one of the types of radioactive decay and very high energy. So that is the electromagnetic spectrum. We're going to talk about how light behaves when it hits an object. Here's an object, and this will be light. Maybe I should use another color, but I don't know if it'll pick up, so I'll use black anyway. Now, here's a 90-degree angle, just for the sake of measurement. Or a pair of 90-degree angles. So this is perpendicular. So if your light comes in at, let's say, like a 45-degree angle and hits this, we're going to start by talking about reflection. Because every time that light strikes an object, it's going to do two things. It's going to reflect and it's going to refract. And we'll talk about refracting in a moment. But reflection, if it hits at a 45-degree angle, that's a percent, not a degree. I was working with percents earlier. Then it's actually going to bounce off and reflect back out at the exact same angle, 45 degrees. Let's say instead, the light source moves up, maybe like there. Now it's coming in at, let's just say, like a, say like a 22.5 degree angle. What angle is it going to bounce back off, reflect back off? It's going to reflect off at exactly the same 22.5 degree angle. And when you shine a light directly on something, then it's going to bounce straight back off at exactly the same angle. So this is what's called the law of reflection. It states that when light strikes something, it reflects at exactly the same angle that it strikes it. And we call, by the way, the angle that the light approaches the angle of incidence. So I'll draw kind of the same thing but horizontally, just because that might help. There's some diagrams where this happens horizontally and some where it happens vertically in the book. So if light comes in at, say, a 45-degree angle, then we're going to call this 45-degree angle, as it's coming in, the angle of incidence. And then when it leaves it, the 45-degree angle, it's leaving it at 45 degrees because it came in, the angle of incidence was 45 degrees. Now we can also talk about refraction. What does refraction mean? It means that every time light strikes an object, some of the light is going to be reflected, but some of it's going to be refracted. And that refraction means it's going to go into the object. It's going to travel into and through the object. So we observe this a lot. I'll actually show you a quick example. Let's take a look at my finger. Actually, you know what? Maybe I'll use a pencil. There we go. Let's take a look at this pencil. I stick it in this glass, and what do you see? You see that the pencil is perfectly straight. And that shouldn't surprise you. It appears perfectly straight. And now, we're going to take the same pencil, same glass. Watch what happens when I pour some water into it. You see something happening, right? Notice the pencil doesn't look perfectly straight anymore. And let's see if I can kind of move this around a little bit. Yeah. So now it looks like it's bending at a certain angle. There's a reason for this. It actually turns out that when light strikes a surface, and we'll just do a dotted line here. So this part is the surface itself. And this dotted line is perpendicular to the surface. Say this is going at 45 degrees because that's an angle of incidence I like using. And it turns out then that when light travels through water, is it going to go as fast or faster or slower than when it's traveling through air? You may recall from earlier in this video that light will actually slow down when it goes from air to water, because light speed in air is 300 million meters per second. Light speed in water is less than that. When an object refracts, when light refracts, I'll say when refracting light slows down, meaning when it enters a medium in which it travels slower, where the speed of light is slower, it bends toward a line that's perpendicular to, and that's like a right angle, to the surface where it entered. In other words, here's the surface. The light as it comes out, it's actually going to bend toward that surface. So it would have normally, like when you looked at the glass that was empty, you had light traveling through the air and bouncing off the pencil, and then in the glass there was still air, and so we had the pencil just going in a straight path because the light hadn't bent. It hadn't refracted in that way. So when we added the water, light of course travels slower through water, so then the light bouncing off, light actually slowed down in the water and refracted toward this perpendicular line. Now, what happens when the opposite occurs? In other words, what happens when light enters a medium where it speeds up? For example, if I had a light that I was shining through this glass of water, then when the light actually comes out into the air, then it's going to speed up and it's going to bend away from this perpendicular line from the surface. So pretend that this was a fish tank. And this is the bottom of the fish tank. And there's no gravel, no sand or anything like that. If I shone a light through the water of the fish tank, then as the light came out the bottom, the light would speed up in the air, and so it would actually bend away from that perpendicular line. You may have noticed in the pencil, it actually, I think it ended up looking more like this, and that's probably because of where the light source was coming from. Let's see what happened. I need to remember. Let's do it again. Yeah, so it seems more like the light, and that makes sense because the light is back there, and so it's traveling through the water and then exiting that medium into the air, and therefore it seems to be bending more this way. So we're observing the light speeding up as it's doing that. You can disregard what I said a moment ago about the light speeding up, that we were seeing the light speeding up coming out, and that's why it bent that way. That's not actually accurate. I was having trouble thinking about the diagram I had because it was a 90-degree angle of this one. So this is actually an accurate picture of what we were doing is we were holding the cup, and you'll see it right here. Like, you'll see the pencil is actually doing exactly what's in the diagram. It's bending this way toward a perpendicular line, and so what I have represented here is it's basically a picture that you have on page 380, but I added a little bit of information just to make it clearer. So here's the angle of incidence of the light, and it's striking this surface. This is the surface that marks where it's entering a new medium, which is water. So it goes fastest through air, slows down in the water, and if it had been going in a straight path, then it would continue and refract at this angle of incidence, which would be about like that. It would continue if it were going from just air to air. But instead, because it's going into water where it slows down, the light bends upward toward this perpendicular line of the surface. It's perpendicular toward the surface. And then here's another one that's perpendicular to the surface. So basically the light goes down at its angle of incidence, then it shifts upward toward that perpendicular line because it slows down. And then when it exits, it'll actually resume the original angle of incidence, more or less, because what happens when light then goes into a medium where it speeds up, it's going to bend back away. So in the water, it was going at about this angle, but now it's going to refract away from that perpendicular line, perpendicular toward the surface. So basically, every time it's entering a new medium, it's going to bend. Now, I'm only showing you part of the picture here because, remember, light does two things when it strikes a surface. Some of the light reflects, and here, this is the full picture, and you don't have a picture in the book like this. It's going to be a mirror image of the angle of incidence when the light reflects. But some of the light will reflect, allowing us to see the wall of the cup. which is the surface it's reflecting off of. But then the rest is refracting in the behavior that we just talked about, slowing down and going toward this perpendicular line. And then when it strikes this surface, which is the other side of the glass, then once again it's going to reflect, excuse me, at the same angle of incidence. It's going to reflect outward. I guess it does actually show all of this in the diagram. So that's the reflection in orange. But then the refraction is going to be, it used to be going in that path, but now it's going to bend away because it's speeding up as it's re-entering air. So this may be a little bit hard to wrap your head around at first, but then again, I tend to be really bad at this kind of spatial thing, like probably worse than the average person, so maybe this is easy to you, it's just hard for me. One more quick thing before we move on. It turns out that when white light, which contains lots of different wavelengths of light, comes through and refracts into something, then what happens is that the different wavelengths are going to refract at different rates because they're traveling at different frequencies, and so they're going to bend in different ways. So when light goes through a prism, and I'm not going to try to make this look realistically like a prism, anyway, just when it enters certain substances, and it might be a prism, but this will also occur to some extent even just when light goes into water, and that's how you can create a rainbow. What's going to happen is the red is going to refract a little differently than the orange. Which will refract a little differently from the green. And they're basically going to separate out. And that's how you can take white light and turn it into a rainbow. Oops. And in the case of an actual rainbow in the sky, the reason it does that is because it'll enter a water droplet on one side and refract, meaning the colors are spreading out, and then it'll bounce off of the other side of the water droplet and refract again, spreading out even farther. And so rainbows are the result of lots and lots of water droplets being hit by light at the right angle, and then that light, as it changes media from air to water, it's going to slow down and refract, and then it's going to come out the other end, and actually what happens is some of the light will be reflected, and then it'll have another refraction occur, and so basically all of that refracting and reflecting is going to generate a rainbow. Or a simpler example, just shine light through a prism, and the prism will diffuse the light out, again separating the different wavelengths. We're going to talk about lenses now in the human eye. So I mentioned before that we see things because light reflects off of an object and then bounces into our eye. Now, it's a little bit more complicated than that. Here's a simple diagram of an eye. And when we see, it's actually because light goes into the eye, and then it goes through this region of the eye, and this is an iris there, like the colored part of your eye. This green is the iris. And this empty space there is the black part of your eye, which is a pupil. And it's not actually that the pupil is black, it's that the pupil is clear, but the inside of your eye is dark, and so what you see is black because the light that comes into your eye is being absorbed largely. So anyway, so light enters your eye, it passes through a lens, and we'll talk about what a lens is, and then it shines back to the this area of your eye, which in the back is called the retina. So all of this orange section on the back of the eye, like on the surface, this is called the retina. Just think of it as like retaining light or something, maybe, I don't know. But yeah, it's just have a related word in the sound of the word anyway. And so once light hits your retina in the back, it can travel through the optic nerve, which is going to carry that signal of receiving the light to the brain, where it's then translated into what you see as light. So basically, the only light that you see is the light that passes in between your irises, or the iris. It looks like two, but it's actually a circle around, it's just one. so that actually passes through the iris, between the iris through the pupil, and then it goes through the lens, and your lens will adjust the angle that the light will travel as it goes to the back of your eye where it's actually picked up. Now, what you want in order to see, I'm going to draw, remember that some light will reflect, so actually even this light that's hitting the surface of your eye, some of it will reflect back in whatever angle is equal to the angle of incidence. So imagine you have, and at any given moment this is true, light coming in from a number of different angles, and as it hits, it's going to kind of converge in, and then this lens, if it's a lens this shape, it's going to converge it even more. But basically, just imagine it passing through the lens. I'm not going to draw it very accurately. And your goal is for it to converge in such a way that it all ends up right on the back of the retina. Like all of it will converge in such a way that the focal point, in other words, one spot where you could actually pick up that whole picture of all the light, that focal point will be right on the back of your eye where the retina is, so then it can travel through the optic nerve to your brain. Now what happens though is when you see something, your eye automatically uses these ciliary muscles. And you may notice that when you stare at something too long, like your eyes get sore, that's because there are physical, like there's literal muscles in your eye that squeeze this lens, and they'll squeeze the lens into different shapes. So sometimes the lens will be, kind of longer, and there are other times when you squeeze the lens and you make it kind of shorter and rounder. And that's because light will diffuse differently through the lens depending on its shape. So let's say something is going on where the light is coming through your pupil, and it converges, but the focal point, the place where it all comes together, is actually not reaching all the way back to your retina. What's going to happen then? Then you're going to have a blurry picture because the focal point is not in the back of your retina. So as you look at that thing, then unless you intentionally look in a middle distance or look at something else, what happens is your eye is going to pretty much automatically refocus, as in contract or expand your lens, so that then the image will become clear, because if you change how the lens is shaped, the light will refract, gosh, I'm having so much trouble with that word, differently until it adjusts and the focal point is right here, where it needs to be at the end of the retina. Now, sometimes you might be nearsighted or farsighted, which means that your eye has trouble actually refracting the light properly to where the focal point is back at your retina. I'll give you an illustration. Let's say that the light is coming through your lens, and it's not focusing quite enough. The light isn't converging enough as it goes through your lens, because maybe your ciliary muscles have just gotten tired of creating that particular shape of the lens that's going to help you see, and instead the focal point would be somewhere over here if the light all converged. If you didn't have a retina to stop it. So you're not going to see very clearly if the focal point would be out there. So what you need then is you need you need a converging lens. Now a converging lens, go a little bit into this. Remember that light, as it hits a lens, what's it going to do? Is it going to speed up or slow down? If it's going from air to basically anything else, it's going to slow down. So this is going to be a glass lens, but in the case of your eye, it's made out of some kind of tissue. And so as it hits, whatever angle it's hitting, draw a perpendicular angle to the surface. Something like that. Actually, I'm not drawing it sharply enough. So here's your surface. Then the perpendicular angle, let's draw it something like that. All right, so that particular point on the converging lens, when light speeds down or slows down, it's going to move toward that perpendicular line, the imaginary perpendicular line. And so that's going to be happening all throughout here, where we have imaginary perpendicular lines and the light is bending toward it. Now, out here, you might be thinking, well, wait a second, how is it that when it goes back into the air, it's actually going to be converging even more? That's because here, it's hitting on the opposite side, and so here is the surface. If we draw a perpendicular line to the surface, it's coming in another direction, and now and so like the light is actually bending away from it. If it had just continued, it would be continuing something like that, but now it's bending farther away from that line because it's speeding up. So toward, then away. So basically, if I drew these perpendicular angles all the way through, you would see that this path of light actually makes sense. It's converging by going toward all of those different perpendicular angles inside of the lens, where it's glass and it's traveling through glass, so it's slower. Then when it exits and goes back into air, it's still converging, but it's at that point moving away from the perpendicular angles of the surface as it's exiting. So it actually makes sense how it works that way. Now, if your eye is having trouble focusing the light to have a focal point on your retina, then you can add glasses. And I'm not going to draw this all out, but that would be a one type of glasses, which would be a converging lens. And so then that's going to cause the light to converge a little bit more there before it even gets to your eye, and then it'll converge even more in the lens, and then the focal point will be right where it needs to be. So that gives your eye assistance if your eye has consistent trouble converging properly. Now, what if the opposite is going on? What if the problem is that your eye is focusing things by converging them too sharply? At this point, you can probably hear Isaac taking a bath very loudly and doing all manner of things to stay awake. Yeah. I wonder what he just did. Now, if your problem is that you're converging the light and creating a focal point too early, then that's also going to cause problems for your vision. And so then you would need a diverging lens. And with this one, with the diverging lens, if we actually figure out where all of the angles of incidence are hitting, like this one's hitting here, so the surface is there, and so a perpendicular line to the surface would be something like this. So this light is bending toward it as it slows down. And then as it exits, it's hitting the surface that's something like that, so a perpendicular line would be somewhere like that. And so if it were going in a straight path, you know, it would be going something like that. Now it's actually bending away as it speeds up from that perpendicular line. I guess I could do that. So this diverging lens will actually cause the light to diverge outward, and you can actually wear glasses that have a slight diverging lens shape, and that's going to cause your focal point to be farther back, which will solve your problem, and then you'll be able to see clearly. So depending on whether you're nearsighted or farsighted, your glasses or contacts will be different shapes and also different thicknesses. So that's basically how a lens will work. That's basically how the eye works, and hopefully that all made sense. I'm going to talk about color and how the eye perceives color. So when light strikes your eye, there are different cells in your eye that will pick up light and others that will pick up color. So rods are the cells in your eye that pick up the difference between light and dark. And then cones are the cells in your eye that discern color. If you watched my video on experiment 15.5, then you'll know that there are 3 different colors of light that your cones will pick up. And you have some cones that are red sensing, you have some cones that are green sensing and some that are blue sensing. So that's only 3 colors, but it turns out your eye can pick up a total of about 16 million colors. How? The answer is that different proportions of red, blue, and green are going to go ahead and mix together into all the different colors. And you may be thinking, well, wait a second, you know, if I was taught that when I was like painting or coloring, the 3 primary colors were red, blue, and yellow. So what's this red, blue, and green about? We'll explain that in a moment. But just know that these are going to be the primary colors, the additive primary colors of light, which is different from, say, paint colors. It's going to work a little differently. Basically what happens, interestingly enough, is when white light strikes an object, remember that some light, anytime an object is struck by light, some light is going to be reflected and some is going to be refracted. So if I have an object which is green, here's the white light hitting it. There's my angle of incidence. I'll just be thorough and have this coming out at the same angle of incidence. Some of the light is actually going to get refracted or absorbed, you could say. And then what comes out is going to just be the color that you see. So if this is a red object, let's say it's absolutely pure red, the purest red possible. As in, like, if your red sensing cones see this, then it's like the absolute exact type of red that your cones were made to sense, with no other mixture, with no blue or green. If that happens, then what's going to happen is white light strikes the object, and red light reflects off of it, and all of the blue and green light are absorbed into the object. So it's not physically going to look like this, but I'm going to pretend that the refracted color is all of the blue and green. So it's not really that you're seeing an object that actually is intrinsically red. What you're seeing is an object that when white light strikes it, only the red light is reflected off. Or on the other hand, if you see like a blue object, what that means is that when light strikes it, all of the red and green are refracted, absorbed, and then all the blue light is reflected off. Now, when you actually have like, when, you know how if you're wearing a white t-shirt, you stay cooler than when you're wearing a black t-shirt? Remember that light has energy. And what happens then is that when you see something white, what it means is that that is not, it's not actually refracting or absorbing, you could say, very much of the light. It's actually reflecting all of the light pretty much. If it's a pure white, it's reflecting basically all of the light. And as a result, like, it stays white because it contains all the different colors. On the other hand, when light strikes something that's really black, you probably hear Isaac. He's tired, poor little man. So when the light strikes a black object, what's happening is that all of the light is getting absorbed into it, and what's reflected off is the absence of color. And so the absence of light. And so then if all the light is being absorbed, then that means all of the energy in the light is being absorbed too. And so that's why black objects get hot in the sun, whereas white objects stay cool. Now take a look in the middle. I've shown where the colors mix. So it turns out that when you have light, if you mix red and green in equal parts, you get a color called yellow, which is not that. This should be yellow, but I don't have any yellow markers. So imagine that this light green is actually yellow. And in between here, if you mix equal parts blue and green, you get a color called cyan. Can't really fit it in there, so I'm going to do that. C-Y-A-N. Oh, that doesn't really show up on the board in the shot. Maybe here will work. Cyan. Yeah, there you go. And then right here, this kind of pinkish color equal parts red and blue of light are going to be magenta. Now these three colors, yellow, cyan, and magenta, where have you heard that combination before? You might know this, but those are the three types of ink that you buy for your printer. And we'll explain why in just a moment. But before we move on, I'm just going to point out early color movies were the result of taking, they would take their footage and it would be black and white. They didn't have the technology to do anything different for their cameras to receive more than light. It's the equivalent of your cameras being eyes that had rods and not cones. At least that's my basic understanding about that. So somebody figured out if you take your movie and you shoot it through three different, like you project it through red, through green, and through blue, then mixing those three colors of light with the footage of the movie would actually produce color. And thus you could actually have color movies back when that was the only way to do it. We're going to close out by talking about these colors that are in the middle. This one, I think I just erased the label by mistake. Magenta. Now when we're dealing with light colors, the primary additive colors, we have red, blue, and green. And when we mix them together, we get yellow if it's red and green in equal parts, magenta if it's red and blue in equal parts, and then cyan if it's green and blue in equal parts. Now, these are light colors, and that's how they mix. And something I forgot to label before is that if you mix equal parts of red, green, and blue, what do you get? You get pure white. Now move over here. This is going to be something a little closer to what you're familiar with mixing colors, but not quite the primary colors you learned in elementary school. So, or probably like preschool, really. Now, in your printer, you have three colors of ink. Cyan, yellow, and magenta. And again, this is the closest I have to yellow. It's kind of a light green. And when you mix all three of those together in equal parts, you get black. Now these are not light colors, these are going to be like ink or paint colors, and those actually will operate differently from light. So it's very different when you take, like, for example, a red light, a green light, and a blue light and mix them together than if you take red dye, or sorry, yellow dye, magenta dye, and cyan dye and mix those together. Now you can get all the different colors out of like ink or paint by mixing cyan, yellow, and magenta in different proportions. And if you mix all three of them together perfectly, you get black. So kind of crazy that the opposite occurs when you mix light colors, the light additive primary colors, and then the subtractive primary colors, which are going to be like your paint colors. So it also turns out, so in the middle of red, green, and blue, you have yellow, cyan, and magenta. Turns out that in the middle of cyan, yellow, and magenta, when you mix those in equal parts, you get green, red, and blue. So the additive and subtractive kind of like, they're like mirror images of each other in interesting ways. So equal parts cyan and yellow mixed will produce green, equal parts cyan and magenta will produce blue, and equal parts magenta and yellow will produce red. Now that's about it for this module. So thank you for listening. The next video is going to be short. This one was really long. There was a whole lot of content in this module. Hopefully everything made sense. Let me know if you have questions. Let me know if I can improve these videos. Sorry that I'm still dealing with glare on the screen as well as lack of focus on the camera. Hopefully the audio is okay. I've ordered better equipment. Some time ago actually I did, but Amazon is backed up for like an entire month. So we'll see what happens. And in the meantime, study hard and miss you guys. Take care.